Two astronomers from Greece have managed to model the three-dimensional structure of an interstellar gas cloud, and found that it's on the order of 10 times more spacious than it originally appeared. The shape and structure of Musca, described in the journal Science, could help scientists probe the mysterious origins and evolution of stars, and by extension, the planets that surround them. Finding the three-dimensional structure of such clouds has been a holy grail in studies of the interstellar medium for many years now, said senior author Konstantinos Tassis, an astrophysicist at the University of Crete. Interstellar clouds serve as the celestial cradles for nascent stars, which condense out of these enormous conglomerations of gas and dust. These cold, dusty, magnetized clouds can reach 1,000,000 times the mass of the Sun. But because they're filled with molecular hydrogen that blocks the light of background stars, they typically appear as holes in an otherwise bright night sky. They're more easily seen using infrared light. But even in infrared light, these clouds are difficult to study because we can only see them as flat structures, even though they're actually three-dimensional. We know very little about how dense they are, what shape they are, and how they're organized inside. All sorts of different physical and chemical processes take place in their interior, and as a result, the process of star formation is poorly understood, Tassis said in an email. How does a giant cloud of 1,000,000 solar masses break up into smaller pieces, and how do these fragments condense into stars similar to our Sun? What makes a cloud form a lot of small stars or a few larger? Only these problems, although they are directly related to the question of the origin of our Sun, our planet, and, ultimately, ourselves, are still very much a mystery, he added. About a decade ago, Paul Goldsmith of the Jet Propulsion Laboratory in Le Canard Flintridge discovered strange hair-like wisps surrounding such gas clouds, rather like the cilia of a bacterium. Amid the chaos of a gas cloud, these ordered structures drew astronomers' attention. How did they form, and why? While doing his doctoral work at the University of Crete, lead author Aristritsis, now a postdoctoral fellow at Australian National University, concluded that these striations were actually caused by magnetic waves leaving their imprint on the cloud's gas. It was then that we realized that these striations might encode a global vibration if the cloud is isolated, a song, a pattern of frequencies that could reveal the true, 3D shape of the cloud, Tassis said. To try and use those magnetisonic waves to understand the shape of an interstellar cloud, they pulled data from the European Space Agency's infrared Herschel Space Observatory, which can see into the infrared. They focused on Musca, which lies in the southern hemisphere roughly 500 light-years from Earth. Musca, a filamentary cloud that's long and thin, made an ideal target because it was relatively isolated. This meant that its striations were unlikely to have been warped by noise coming from nearby structures, Tassis said. Because the waves are basically trapped within the interstellar cloud, the wavelength will actually hold information about its dimensions. After using the striations to determine the wavelength of this global vibration, the scientists were able to determine what the true shape of this gas cloud was. From our vantage point, Musca looks like a needle. But the magnetisonic waves revealed that the gas cloud was actually shaped like a pancake, one that we were viewing edge on. All in all, the cloud seems to measure roughly 24 light-years wide by 18 light-years across and 1 light-year thick, in much the same way that a piccolo flute makes a much different sound than a tube. The air vibrates with different frequencies in the two cases because the shape and size of the instruments are very different. A pancake-shaped cloud vibrates in a tune that is very different than that of a needle-shaped cloud, Tassis said. Musca very clearly vibrates like a pancake, not a needle. It is not a subtle effect, it is eye-popping. This meant that the gas cloud was far more voluminous than they had previously thought, roughly on the order of 10 times larger, Tassis said. And because the same amount of gas filled that bigger than expected space, it meant the cloud was much less dense than scientists had expected. It was a huge surprise to us, Tassis said. Musca has been considered the prototype filamentary, needle-like cloud. Instead, it is really a pancake, seen on its side. This completely alters our understanding of the balance of forces acting on Musca, and mediating its process of forming stars. For one thing, a less dense gas cloud would have a much lower rate of star formation. On top of that, the molecular demographics of sparser clouds are different from denser ones. Dense clouds, for example, are more likely to have nitrogen-based molecules such as ammonia. The shape of such a cloud can be very telling, too. Magnetic forces make pancake-like clouds, turbulence forms needle-like clouds, and thermal forces result in roundish, blobby clouds, Tassis said. If scientists can now start to render more of these clouds in 3 dimensions, they won't mistake a pancake-shaped cloud for a needle-shaped one. That means they'll start to have a much better sense of the forces at play. Now that we know Muska is a pancake, we know that at least for this particular cloud, magnetic forces must play a key role in the star formation process taking place in its interior, Tassis said. Armed with knowledge of Muska's three-dimensional structure, other scientists can now draw out more information about the chemical and physical properties of this interstellar gas cloud. With its 3D structure revealed, Muska will now act as a prototype laboratory to study star formation in greater detail than ever before, Tassis said. The Muska star formation saga is only now beginning, and this is a very exciting development that goes beyond this particular discovery. Caption: Watch this robot, a combination of industrial robot arms, parallel grippers, force-detecting sensors and a 3D camera, will assemble an IKEA chair in about 20 minutes. Suarez Ruiz, Joe, FAMS Sci. Robot 3, EA8063852018. Watch this robot, a combination of industrial robot arms, parallel grippers, force-detecting sensors and a 3D camera, will assemble an IKEA chair in about 20 minutes. Suarez Ruiz, Joe, FAMS Sci. Robot 3, EA8063852018. Caption: NASA is planning to launch its Transient Exoplanet Survey satellite in mid-April. TESS will help scientists study exoplanets that orbit other stars. The trick is to watch them as they pass in front of their host stars. NASA is planning to launch its Transient Exoplanet Survey satellite in mid-April. TESS will help scientists study exoplanets that orbit other stars. The trick is to watch them as they pass in front of their host stars. Caption: Sophie, a remotely controlled robotic fish, explores the Somazomos Strait in Taveuni, Fiji. Sophie, a remotely controlled robotic fish, explores the Somazomos Strait in Taveuni, Fiji. Caption: Scientists uncover cave art created by Neanderthals. Scientists uncover cave art created by Neanderthals. Caption: A video recorded in 2016 by a polar bear wearing a GPS collar equipped with a video camera. This bear lives on the sea ice of the Beaufort Sea. Credit: USGS and Polar Bears International. A video recorded in 2016 by a polar bear wearing a GPS collar equipped with a video camera. This bear lives on the sea ice of the Beaufort Sea. Credit: USGS and Polar Bears International. Amina.Khan at latimes.com. Follow it Aminorite on Twitter for more science news and like Los Angeles Times Science Health on Facebook. More in science.